Predicting flood inundation in Calgary and Minneapolis using logistic regression. In 2013, Calgary experienced a major flood. The estimated damage to city-owned properties and infrastructure was $500 million, and to city parks alone there was an estimated damage of $55 million. 100,000 Calgarians evacuated from their homes. This was a terrible disaster, and cities need to be prepared to deal with more floods as rain events become more extreme due to climate change. We took it upon ourselves to create a flood prediction model based on Calgary's flood to help cities predict these future disasters. To build this model, we followed a well-defined workflow. We first built a model using variables selected systematically. We then cross-validated the model to make sure that the model was generalizable to the whole city. Additionally, we performed a spatial cross-validation to see how our model performed in different neighborhoods in Calgary. Lastly, we applied this model to Minneapolis to predict inundation in a future flood scenario. We used ArcMap and R to complete this project. In ArcMap, we gathered different variables in this systematic process, and we used ArcHydro tools to evaluate the hydrology of Calgary. In R, we selected variables that we had created in ArcMap using the different selection processes, and then validated the models and assessed their fitness. We then used the final model to predict future inundation in Minneapolis. We selected 4 different types of variables that we thought might be correlated with flooding. These were geographic variables, spatial variables, hydrological variables, and census variables. The geographic variables we selected were elevation, slope, and land cover. All these variables were included in our final model. The spatial variables we selected were distance to water, distance to steep slope, and distance to development. All of these variables were also included in our final model. The hydrological variables we looked at were flow accumulation, flow length, and basin. The only variable used from this group was the flow accumulation. From census data, we looked at the total population, the income, employment rates, and households. We used all of those variables as well. The model that we created generated a gradient of probabilities from 0 to 1. The area under our curve, which compares our model's ability to discriminate between flooded and not flooded cells, was 0.91, which implies that it was a very strong model. The confusion matrix shows the classification of true and false positive and negatives. We chose a cutoff value of 0.08, which optimized the highest number of true and positive and true negative returns. Here, we can see that there are about 1,200 false positives. That is okay because we want to be predicting more areas are flooded to keep more people alert. The density plot on the right shows the probability assigned to pixels which were flooded and not flooded. The plot shows that the model is very good at predicting not flooded pixels, but not as good at predicting flooded pixels. Here we have 3 maps. On the left is the map of the actual inundation that occurred during the 2013 flood. This also includes water features and areas that were not inundated. In the middle, we have a map that shows the predicted inundation based on the model that we created. Areas that are lighter are areas where there is no predicted inundation, whereas areas that become darker green are areas where there is more likely to be inundation in a flood. Then, using the same cutoff value of 0.08, we classified cells in Calgary where there was flooding or where there would not be flooding in our predicting model. We also did a spatial cross-validation as mentioned earlier. This looked at different neighborhoods across Calgary and compared their mean absolute error. What we see is that neighborhoods that were closer to the actual inundation had a higher mean absolute error than areas that were further away from the actual inundation. This is because there was more variation in the cells in the actually inundated neighborhoods, and therefore it was harder to make an accurate prediction, whereas areas that were further away from the actual inundation mostly had cells that were not flooded or had a value of 0, and their mean absolute error was therefore very small. We then applied this model to Minneapolis. We selected the city of Minneapolis because it has the Mississippi River running through it, similar to the river that runs through Calgary. These 2 rivers are of the same width, about 200 meters across. We included the water features in Minneapolis because we wanted to demonstrate how important the water features are in predicting inundation in the model. As you can see, it seems that the probability of inundation dramatically decreases the further away you get from water features. So we know that the model relies heavily on water features, but we do believe that it is still a strong model in predicting future inundation.